All right, everyone. Well, thanks for being here. I'm Jacob. I'm an assistant professor at Georgia Tech, and this is joint work done with my collaborators, Ignacio and Jan, who are at the Department of Energy. And I'm here to tell you why scientific computing needs program analysis. So partial differential equations are everywhere, whether you want to model things like fluid flows or electromagnetic effects, or even traffic congestion. All of these processes are described by partial differential equations, or PDEs for short. Now, in particular, these examples all fall under the umbrella of hyperbolic PDEs. Now, I realize that this is a lot of terminology to throw at you, so as just a brief roadmap of how we're going to get to a point where we can make sense of things, is that we're going to define what these equations are, then we're going to show how one solves these equations, and that will allow us the necessary background to understand how to analyze those solvers, and then we'll be able to see how to use that analysis for end-to-end verification. So the requisite PDE background is as follows. You may be wondering, what is a hyperbolic PDE? Well, the hyperbolic PDEs that we're going to consider are partial differential equations of this form, where you have a time derivative and a spatial derivative. And the solution u is a function of both space and time, and it quantifies where the wave is at different points in time. Now, we also see this function f, which is known as the flux function, and it governs how the wave flows. And it's typically a nonlinear function. So why are these PDEs so interesting? Well, it turns out that nonlinear function leads to a lot of nonlinear behavior, which can even manifest as shock waves forming in the PDE. Now, these PDEs are also interesting because there's a lot of key numerical properties that must be satisfied. And the waves transmit at a finite propagation speed, which we'll see later why that's important. So going back to our roadmap, having now defined what these PDEs are, now I want to talk about how one actually solves these PDEs. So how are hyperbolic PDEs solved? Well, you might try to whip out a pencil and paper, but you won't get too far because these PDEs tend to be very intractable to solve analytically. So what you have to do instead is resort to numerical methods. And these typically involve some kind of discretization that you then implement as a computer program. Now, our work will focus on analyzing those programs. And why do you want to analyze these programs? Well, there are a lot of things that can go wrong with these programs. For instance, they can introduce artificial wave dissipations, they can introduce artificial oscillations, they can even experience things like overflows due to some of these numerical properties being violated, and shock waves, and many different things can go wrong. And so this is really a broad new class of numerical bugs that extends beyond traditional floating point errors. So wouldn't it be great if we could verify the absence of these bugs? Well, we can do that if we use formal verification. So before getting to that, let me just give an overview of how these solvers actually work so we know what we're actually going to verify. So what we'll do is we'll discretize our physical world into the computational domain. So that means we discretize space as well as time. And so we get these discretized mesh points at different points in space and time. Now, how do we compute those mesh points? Well, that's where finite difference schemes come into play. So we have the Lax-Friedrich scheme, the leapfrog scheme, and the upwind scheme. Now, there are other schemes besides these, but our paper focuses on these three. So the idea here is that we're going to compute the n+1th time step as a function of all of the earlier time steps. And then we can actually take that process and implement it in code. And we see that there's this natural loop that loops over the different time steps that encodes the finite difference scheme. So now going back to our roadmap, having talked about what hyperbolic PDEs are and how they're solved, now we're laying the groundwork to discuss how to actually analyze the code, which is really our core contribution. So our tool is called Focus, and the overview is as follows. So if we go back to these schemes, we'll have some code implementation, and then we're going to analyze that code using abstract interpretation. Now, we're also going to use numerical optimization techniques as well for reasons that I'll now describe. So here we have that Lax-Friedrich scheme. Now, our goal is to get precise bounds on the set of values that those mesh points could take on. So naively, you might think about doing some kind of interval arithmetic where you would abstract the values of these individual operations, like these additions and then these subtractions, and just compose those intermediate results again and again until you get your final answer. But the problem is that the imprecision would accumulate. So rather than this imprecise strategy, we want something better. We want a tighter bound on the values that this mesh point can take. And so we want to actually optimize for a tight enclosure for the entire stencil. And that's the core idea behind our tool Focus. And we want this not just for the Lax-Friedrichs, but also for the leapfrog scheme and the upwinding scheme as well. So how do we actually optimize for these tight enclosures? Well, this is where continuous optimization saves the day. So this is really inspired by a lot of deep neural net verification works. And so our strategy will be to find a linear approximation of that finite difference scheme, bound the approximation error, and voila, we get abstract transformers that are sound for any linear abstract domain. So here we have the Lax-Friedrich stencil for the cubic flux function. And if you were to plot what that finite difference scheme looks like as a function of the mesh points, you get this nonlinear curve. But it turns out a linear approximation is pretty good. And so we can find one, and then all we have to do is get a sound enclosure around that linear approximation. And so that means we have to compute this term D. Now, we want the tightest such D to give the tightest bound. And that involves solving this non-convex optimization problem, which seems a little tricky, but actually using clever techniques from the optimization literature, we're able to make it tractable. Now, going back to our roadmap, having talked about how these PDEs are solved and how we can analyze those solver schemes to get precise bounds, I want to describe now how we can actually use those results for full end-to-end verification. So what properties can these PDE bounds verify? So we can reason about the robustness of the PDE to different initial conditions. So if you run the PDE with different initial values, what will the solution look like after a certain number of time steps? And if you want to get a robust range, well, you can use our analysis. Another key property is the CFL condition, which is a very important property for understanding the stability of the solver, because it relates the wave speed to the mesh discretization that you've chosen, and it must be satisfied at every iteration of that for loop that I described, and so really, it's a loop invariant. We also formalize the notion of total variation, which characterizes the amount of spurious oscillation and dissipation. And we also want to verify the absence of shock waves forming. And so given these four properties, if we have tight bounds, we can actually verify all of them. So you may be wondering, how well does this technique perform in practice? Well, we did an evaluation to see where we compare against like the standard abstract transformers with the zonotope domain, and the standard abstract transformers compose all the primitive operations together. And we'll see how that leads to imprecision. Now, we also solved the PDE for concrete sampled inputs as a sanity check, and I'll describe that later. And we measured the runtime, the bound precision, and we verified the properties that I described earlier. So we looked at 6 different partial differential equations where we have these different flux functions, and noting that the form of the hyperbolic PDE, the flux functions will be substituted in for that f of u. In fact, that's also what gets substituted in the finite difference scheme. So I'm going to focus now on the results for the Burgers PDE. So here we have the results for simulating the Burgers PDE with the Lax-Friedrich scheme. Now on the x-axis is the point in space, and to denote different time steps, we have these 4 different plots. So we have these green bounds that represent the values of concrete samples. So the desired behavior is to, as tightly as possible, enclose these green bounds. And this is really our sanity check, because any sound method should enclose these. So the naive bounds are sound, but they're not as precise as our bounds at enclosing those green dots. So the effect is even more pronounced if we look at the leapfrog scheme for the same Burgers equation. We see the naive bounds are very loose, and they're too imprecise to be able to verify the absence of shocks, nor can they verify the CFL condition. In contrast, R bounds are much more precise and can verify no shock waves as well as the CFL condition being satisfied. Similarly, in the upwind finite difference scheme, we see that the naive method is very imprecise and cannot verify the properties, whereas our method, Focus, is much more precise and can verify those properties. And so even on different benchmarks, we see the same trends. And so as a measure of scalability, we also looked at what happens if you run for hundreds of time steps. And so in this benchmark, we ran it for 280 time steps, and this is about a little over 5,000 total mesh points. So about over 5,000 variables in your abstract program state. And we see the bounds are still very, very tight. And so in summary, we started with the notion of a hyperbolic PDE. We showed how those hyperbolic PDEs are numerically solved, and that allowed us to talk about our contribution of statically analyzing those solver codes, and then using those results for end-to-end verification of formal properties over PDEs. And so our tool Focus is the first abstract interpretation of hyperbolic PDE solvers that uses these precise linear bounds, and it's the first to verify these PDE-specific properties for scientific computing correctness. So on that note, I will take questions. Thank you.
Does it work? Okay, very nice talk.
Thank you.
I'm Chen from UC San Diego,
okay.
And I'm actually working on probably the same problem, but in a different domain. We synthesize abstract transformer for compiler, data flow analysis in compiler.
Okay.
So I think we're also trying to identify the common pattern in the compile code, just like you synthesize a transformer for those complex function you show in as a large box to avoid the imprecision decreasing.
Yeah.
So I'm wondering, like, did you manually discover this kind of pattern, or you have some way to automatically find this pattern, like in your PDE setting?
Yeah, great question. So did we manually find these patterns, these different finite difference schemes, or is there a way to automatically figure out what's a good pattern to design something more precise for? So for these, we did just kind of manually play around with different finite difference schemes and found that these ones had the nice properties that allowed the optimization to be precise and sound. And so we haven't explored yet if there's an automated way to figure out new types of expressions for which you could find a more precise bound. But I think that'd be a great future direction. Yeah, it's a great idea.
Oh, great. Thank you. If nobody, can I ask a second question?
Sure, of course.
So whether your synthesizer transformer always reach the tightest bound, or you just want them to be as tighter as possible?
So it's not the tightest bound, because with zonotopes there is no most precise abstract transformer for the zonotope abstract domain. But for the given linear regression plane, we get the most precise bound for that particular plane. But whether or not there's a different linear regression that's more precise, it's not really possible to say with the zonotope abstract domain, because they don't have what's known as a most precise abstract transformer. So it's probably more the latter. It's like as precise as possible. Yeah.
Got it. Thank you.
Awesome. Thanks.
All right, let's thank the speaker again.